Welcome to the third lecture of statistical inference. As you recall, in the previous lecture, we learned about different sampling distributions and we learned classical methods of statistical inference. In that lecture, we learned about one method of statistical inference, that is point estimation. Okay, in point estimation, what we did there, we estimated the population parameter directly from the sample information. Second method is confidence interval. Confidence interval. That we will discuss today. We will discuss and do examples related to confidence intervals in various cases of sampling distributions. So first, let's see what's a confidence interval is. A 100 into 1 minus alpha percent confidence interval for a population parameter theta, 100 into 1 minus alpha percent confidence interval, shortcut we will write CI, for a population parameter theta is a random interval L1 to L2 such that probability of theta lying in this interval is equal to 1 minus alpha. Okay, you can say it other way. What is 100 into 1 minus alpha percent confidence interval for a population parameter theta? It is an interval L1 to L2 such that probability of lying of theta in the interval L1 to L2 is 1 minus alpha. If probability of theta in this interval L1 to L2 is 1 minus alpha, we say that L1 to L2, this closed interval, is 100 into 1 minus alpha percent confidence interval of theta. Is that fine, the definition?
Yes, sir.
Okay.
Yes, sir.
Now let's see confidence interval for mean of normal population with non-variance. First case, CI confidence interval of mean of normal population with non-variance. Suppose a random sample x1 to xn is chosen from a normal population with mean mu variance sigma square, where mu is unknown, for which we are interested in finding confidence interval. Okay, sigma is known to you. So on the basis of this random sample, we need to determine confidence interval for mu. That's the task here. So recall that this random sample is taken from this normal population. So sample mean follows which distribution? Normal distribution with mean mu and variance sigma square over n. Right? X bar follows normal distribution with mean mu and variance sigma square over n. That means what? The statistic x bar minus mu over sigma over root n is a standard normal variable. Standard normal variable means Z follows normal distribution with mean 0 and variance 1. Okay. So in this situation, Z equal to x bar minus mu over sigma by root n is a standard normal variable. We will use this statistic to find confidence interval for mu. Let's see how. Z is following normal distribution with mean mu or with mean 0. So can I write this probability of Z lying in the range Z alpha by 2 less than equal to x bar minus mu over sigma by root n less than equal to Z alpha by 2 is 1 minus alpha. You should understand the meaning of Z alpha by 2. Z alpha by 2 is the value of Z such that probability to the right of it under the normal curve is how much? Alpha by 2. Because normal distribution is symmetric, this value is minus Z alpha by 2. So this probability is also alpha by 2. This is your mu, you can say, in terms of x. So this is the interval. What is the probability under the curve in this range? In this range, it is 1 minus alpha. Probability from minus Z alpha by 2 to plus Z alpha by 2 is 1 minus alpha, clearly. Okay, so this statement is fine. Now, simplify this inequality for mu. Multiply throughout by sigma by root n and then see what do you get. I think you will get x bar minus Z alpha by 2 minus Z alpha by 2 sigma times or sigma over root n less than equal to mu less than equal to x bar plus Z alpha by 2 sigma by root n equal to 1 minus alpha. Just check it. Is this simplified inequality fine?
Yes, sir.
Okay.
Yes, sir.
So now see what is the 100 into 1 minus alpha percent confidence interval for mu. This interval, this is your L1 and this is your L2. Because probability of mu lying in this interval is 1 minus alpha. So these two limits form the boundaries of your confidence interval. So I can write it separately now. But before I write it finally, you should look the situation again. You have taken a random sample from a normal population with known variance. Then you know Z equal to x bar minus mu over sigma by root n is a standard normal variable. Using this statistic, you have written this probability equal to 1 minus alpha. Okay. After that, you have simplified this inequality to get confidence interval for mu. All right. So I'm writing it again. Then we will do one example. So 100 into 1 minus alpha percent confidence interval for population mean is x bar minus z alpha by 2 sigma over root n. Upper limit is x bar plus z alpha by 2 sigma over root n. This is your L1 to L2. 100 into 1 minus alpha percent confidence interval for the population mean mu. Notice that I have replaced capital X bar by small x bar because when I will write interval, I need to give the value of the statistic. Okay, capital X bar, but when I'm writing interval, I am replacing it by small x bar. Okay, now let's see one problem. Take out your calculators, please, that will help. So I'm writing this example. Find the 95% confidence interval, 95% confidence interval for mean of population with variance sigma square equal to 9 from the following sample. I'm writing the sample values 8, 13.6, 13.2, 13.6, then 12.5, 14.2, 14.9, 14.5, 13.4, 8.6, 11.5, 16, then 14.2, 19, 17.9, and 17. This is the given sample. Using this sample information, you need to find 95% confidence interval for the population mean where the variance is 9. And given that the population is normal, okay? So formula is written here. You should think what do you need to calculate. In this interval, what do you need? X bar, sample mean that you can calculate from this given sample. What is the sample size here? 25 or 16? 16. Sample size is 16. There are 16 points that you will need here in this formula. Calculate X bar. Sample mean, just add all these 16 numbers and divide by 16. See what do you get. Do you get 13.88? Hmm?
Yes, sir.
Yes, sir.
Yes, sir.
Okay. 13.88, you get X bar, sigma is 3. 95% confidence interval is needed. So from where you will see Z alpha by 2, 95% means what? This is normal distribution. Z alpha by 2, 95% means 2.5% this side, 2.5% this side. 2.5% means 0.025, right?
Yes, sir.
Okay, so this value you can see from the normal table. And you will find it 1.96. Okay, so usually the interval is asked 95% or 99% like that. So just if you remember standard values, that's fine. Otherwise, you will get it. You will have to see it from the normal table. Okay, so Z alpha by 2 is also obtained. Z alpha by 2 means here Z 0.025, it is 1.96. Now you can calculate your L1 and L2. L1 means this, X bar minus Z alpha by 2 sigma by root n. Just substitute the values and see what do you get. Do you get 12.41 for L1
Yes,
and
sir.
12,
Yes, sir.
15.35 for L2?
3, 4,
Yes, sir.
4.
1.3.
Okay, if it is 99%, then just Z alpha by 2 would change. All right.
Yeah.
Okay, so you have understood how to find confidence interval for population mean in case the population is normal and its variance is given. Let's move to the next case. One more thing, in the case when sigma is not given and sample size is large, then what should you do here? You can use the sample variance. Okay. If population variance is not given, but sample size is large enough to use central limit theorem, in that case you can use S square in place of sigma square to write your confidence interval. Okay. Let's see the next case. This time confidence interval of mean of normal population with unknown variance. Confidence interval for mean of normal population with unknown sigma square. One more thing, sample size is less than 30, small sample. Because if sample size is large, then I've already told you, you could use S square in place of sigma square.
Yes, sir.
So what do you think, which statistic will work in this case for finding confidence interval for mu?
T distribution, sir.
T
Can
distribution.
use the T distribution.
Yes. Do you recall which statistic? It is x bar minus mu over S by root n. This statistic follows T distribution with n minus 1 degrees of freedom.
Yes, sir.
T distribution with n minus 1 degrees of freedom. All right. We will use this statistic to find confidence interval for mu in this case. You should know about T distribution. Its shape is similar to normal distribution. It is symmetric about T equal to 0. So if here you have T alpha by 2, here it should be minus T alpha by 2. This side probability, this region is alpha by 2, probability is alpha by 2, this side also alpha by 2. So you can write it further that probability of this statistic, because it is following a T distribution, so probability of this statistic lying in the interval minus T alpha by 2 to T alpha by 2 is 1 minus alpha. Lying in this interval is 1 minus alpha. So simplify it again for mu to get the confidence interval. See what do you get. It is similar to the calculation that you have done in the previous case. So see what you get, the lower limit of the confidence interval. You get x bar minus T alpha by
T
2
alpha by 2 sigma over root. S over root n.
S
S
over
over root n.
upper limit x bar plus T alpha by 2 S over root. Okay, let's see one problem. Okay, claim it, just keep L1, L2. Example is find the 95% CI of mu of a normal population based on the sample of size 24 given below. 24 is less than 30, and also sigma square not given. Let me write the given sample first. 52.7, 43.9, 44, 41.7, 71.5, 47.6, 55.1. Then 62.2, 56.5, 33.4, 61.8, 54.3, 50, 45.3, 63.4, 53.9, 65.5, 66.6, 70. Final row is 52.4, 38.6, 46.1, 44.4, 60.7, and 56.4. Okay, this is the given sample. Now, clearly n is 24. X bar you will determine. And you need to determine S also, sample standard deviation. So how much you get for X bar? I'm writing here, you can verify it later. It's 53.92.
53.92, yeah.
And sample standard deviation, you get 10.07. Okay, so we need 95% confidence interval. It means, what do we need? X bar minus T alpha by 2. T is 0.025. S over root n. In this case, X bar is 53.92. T is 0.025. You have to see from the normal distribution table. For how many degrees of freedom? N minus 1 degrees of
23.
freedom. Yeah, here
23.
23 degrees of freedom. So for 23 degrees of freedom, you need to see the value T 0.025. That you will get from the T distribution table. And this value is 2.069. This value is 2.069. You can check it from the T distribution table. Okay, so after that, you just put the value of X bar, T 0.025 and S, and then value of N. After doing all the calculation, you get 49.67. And for upper limit calculation, similarly, there is plus only. For upper limit, you get 58.17. Is it fine?
Yes, sir.
Okay, just you need to
Yes, sir.
verify the calculation. That's it. Otherwise, you understand the concept that how to find the confidence interval in such a case. So let's see the third case. Confidence interval of variance of normal population, CI of sigma square of normal population. With unknown mean. So suppose a random sample x1 to xn is taken from a normal population with unknown mean. So which statistic you learned that involves sigma square on the basis of sample? A random sample is taken from normal population with mean, mu, variance sigma square. Mu is unknown, sigma square is also unknown. We are interested in finding confidence interval for sigma square. So which statistic involves sigma square that we can use for finding confidence interval of sigma square? If the sample is taken from normal population, recall that the statistic n minus 1 s square over sigma square follows chi-square distribution with n minus 1 degrees of freedom. Do you recall it?
Yes, sir.
Why are we using it? Because it involves sigma square. Rest n and s
Yes,
square
sir.
we can obtain from the sample. Okay. So we will use this statistic to find confidence interval for sigma square. Before that, you should understand the scope of chi-square distribution. Chi-square distribution is not symmetric like normal distribution. It could have any shape. Okay. It is not symmetric about something. Okay. So suppose this is the value of chi-square random variable such that probability to the right is alpha by 2. And you need to search a value here such that the probability to the right is 1 minus alpha by 2. Probability to the right is 1 minus alpha by 2. So what is the probability to the left? Alpha by 2. Getting?
Yes, sir.
So because it is not symmetric, you have to see both the values. You have to see both the values from the chi-square distribution table.
Yes, sir.
So just understand the meaning. Chi-square alpha by 2 means the value of chi-square random variable such that probability to the right of this is alpha by 2. And chi-square 1 minus alpha by 2 means value of the chi-square random variable such that probability to the right of this is 1 minus alpha by 2. So that probability to the left is alpha by 2. And
Yes, sir.
probability in the remaining region is 1 minus alpha that we are interested in. Okay. So what should I write then? Probability of this chi-square random variable n minus 1 s square over sigma square lying in the interval chi-square 1 minus alpha by 2 to chi-square alpha by 2 is how much? 1 minus alpha. That's clear. Now just simplify it to get confidence interval for sigma square. Just revert the middle expression and solve for sigma square. What do you get? N minus 1 s square over chi square alpha by 2 less than equal to sigma square less than equal to n minus 1
N
s
minus
square
1.
over
Chi square
chi-square
alpha by
1
2.
minus alpha by 2, right?
Minus alpha by 2.
So now you understand what is your confidence interval. It is n minus 1 s square chi-square divided by chi-square alpha by 2 to n minus 1 s square chi-square 1 minus alpha by 2. So now we will do a problem on it. I'm writing the interval here, L1 to L2. It is n minus 1 s square chi-square alpha by 2 to n minus 1 s square over chi-square 1 minus alpha by 2. Okay, now let's see a problem on it. Find 95% CI for sigma square of a normal population based on the following sample. The sample is 3.4, 3.6, 4.0, 0.4, 2, then 3, 3.1, 4.1, 1.4, 2.5, then 1.4, 2, 3.1, 1.8, 1.6, then 3.5, 2.5, 1.7, 5.1, 0.7, 4.2, 1.5, 3, 3.9, and 3. So this is the given sample. From the sample information, you need to find 95% CI of sigma square. See what is 95% CI from that formula in your problem. What is n here? 25. How many points are there in
25.
the sample?
25. N is equal to
24.
25.
So
Yes,
you
sir.
can write here 24. S you have to find. Sample standard deviation you have to find. Its value is, I'm writing here, 1.408. This is the value of small s. Chi-square chi-square alpha by 2, you need 95%. So you need chi-square 0.025 to 24 into 24 into 1.408. Chi-square how much? 1 minus alpha by 2 means how much? 0.975. Okay, these two values you will see from the table. This is chi-square 0.025 and this is chi-square in your problem 0.975. So from the table if you see, you will get for 24 degrees of freedom. Total number of points in the sample is 25. So for 24 degrees of freedom, value of chi-square 0.025 is 39.4 and value of chi-square 0.975 is 12.4. Okay. You see this chi-square value is towards the left, so naturally value is smaller here. Okay. Towards the right, it's greater. All right. So just substitute these values here and see what do you get. You should get 0.858 lower limit of the confidence interval and 2.725 upper limit. Just check it.
Yes, sir.
Okay. So now we move to the next case. Confidence interval of difference of population means. CI of difference of population means mu1 and mu2. Suppose you have two populations. You want to know the confidence interval of the difference of their means mu1 minus mu2. What is given to you? Two random samples are given of sizes n1 and n2. Say mean of the first random sample is x1 bar, mean of second is x2 bar. Okay, two random samples of sizes n1 and n2 are chosen from two normal populations. I'm considering normal populations such that mean of first random sample is x1 bar, second is x2 bar. And let's say the variances of the population are given to you. Sigma 1 square, sigma 2 square. After that, I need CI of mu1 minus mu2, difference of the population means. So I need to construct a statistic that involves mu1 minus mu2. That we did in the previous lecture. Hope you recall that the statistic x1 bar minus x2 bar follows a normal distribution with mean mu1 minus mu2 and variance sigma 1 square over n1 plus sigma 2 square over n2. Again, I repeat, two random samples of sizes n1 and n2 are chosen from two normal populations with mean mu1 and mu2 and variances sigma 1 square and sigma 2 square. Mu1, mu2 are not given to you, but sigma 1 square, sigma 2 square are given. After that, we are interested in finding confidence interval of mu1 minus mu2. In this situation, x1 bar, the statistic x1 bar minus x2 bar follows a normal distribution with mean mu1 minus mu2 and variance this square root of, without square root, I'm saying variance sigma 1 square over n1 plus sigma 2 square over n2. It's very easy to think. Let me remind you what you did in the previous lecture. The statistic is x1 bar minus x2 bar. These are sample means. Sample means are normal random variables because these are taken from normal populations. Difference of two normal random variables is again a normal random variable. And mean of this normal random variable is very easy to check. If I take expectation of this, what I get? Ex1 bar minus ex2 bar. That should be mu1 and mu2 because a sample mean follows the distribution with the same mean as of the population. And so I can write it mu1 minus mu2. Likewise, variance of x1 bar minus x2 bar. Variance of x1 bar plus variance of x2 bar. What is variance of x1 bar? That is sigma 1 square
Sigma
over
1
n.
square of 1.
Yeah. Variance of x2 bar is sigma 1
Sigma 2 square by
over
n2.
n2. So it's simple. You can check it. Okay, so because it is a standard normal variable, you can say that thing again. Which thing? That probability of Z lying in the range minus Z alpha by 2 to Z alpha by 2 should be 1 minus alpha. Substitute your Z here and simplify this inequality for mu1 minus mu2. So it's easy to simplify and write your confidence interval. I'm writing here L1, L2, or the difference of population means it is x1 bar minus x2 bar minus Z alpha by 2 square root of sigma 1 square over n1 plus sigma 2 square over n2. Okay, Z alpha by 2. This, all right, after that, just do the plus sign here means x1 bar minus x2 bar. Check it whether I've written correctly or not. Is it fine?
Yes, sir.
Yes, sir.
Okay, so
Yes,
this
sir.
is the 100 into 1 minus alpha percent confidence interval for difference of population means mu1 minus mu2. So if two random samples are given, you will find x1 bar, x2 bar. And let's say if you need 95% confidence interval, you know the value of Z alpha by 2. And random samples are given from the populations where variances are also known. So you will know sigma 1, sigma 2, then n1, n2. Finally, just substitute everything into this formula to get the confidence interval. Okay. So one example is given in the lecture notes. Please see this. It's a matter of calculation only. Okay. So I'm moving to the next case. CI of population proportion, confidence interval of population proportion. What is in this? Suppose you have a binomial population with probability of success P. You know, in a binomial distribution, each trial has a constant probability of success. So for the whole binomial population, we are assuming that probability of success is P. After that, a random sample is taken, or you can say n trials are performed, and suppose you obtain x successes. Out of n trials, you get x successes. So on the basis of sample, what is the proportion of success? X over n? On the basis of sample, the proportion of success is x over
Excellent.
n.
Next over.
Let's denote this statistic by p cap. This is the proportion of success on the basis of sample, and this is the success proportion in the population. Okay. So we are interested in finding CI of small p. So we will use this statistic. So for that, you need to know the distribution of this p cap statistic, x over n. If you recall, a binomial random variable follows normal distribution under certain conditions. The conditions are np is greater than equal to 10, np is greater than equal to np into 1 minus p is greater than equal to 10. Under these conditions, the binomial random variable can be approximated by normal random variable. So what I'm trying to say that x follows under these conditions, x follows normal distribution with mean NP and variance NP into 1 minus p. Okay, this is the result that you have done when you did normal distribution. You studied binomial as an approximation of normal distribution as an approximation of binomial distribution. This you have done earlier. Okay, so x is here a binomial random variable. It follows under these conditions normal distribution with mean NP and variance NP into 1 minus p. So from this information, we can think about the distribution of p cap, the sample proportion. So what do you think? X over n will follow which distribution? It's a linear combination of a normal random variable. 1 over n is simply constant. It is again a normal random variable. Okay, we discussed it in the previous lecture. So it follows which distribution? P x over n follows a distribution with mean p and variance p
Into
into
1
1 minus p over n.
over n
Because here it divides by 1 over n
n
square.
square.
Yeah. So p cap follows normal distribution with mean p, variance p into 1 minus p over n. Good. So from this we can proceed further to get confidence interval for p. How? Because it is a normal random variable. So its probability, not its probability, the corresponding standard normal variable probability is 1 minus alpha in which interval? Z minus Z alpha by 2 to plus Z alpha by 2, but which statistic you will write here? P cap minus P over sigma by root n means this is your sigma square, correct?
Yes, sir.
Is it your sigma square?
Yes, sir.
Sigma square. Yeah.
So you need to write sigma here, not sigma by root n, because it's not a sample. We are talking about this random variable. Okay, so you can write here P into 1 minus P over n. This is 1 minus alpha. Because p cap is a normal random variable with mean p and variance this. So this is a standard normal variable. So its probability in the interval minus z alpha by 2 to z alpha by 2 is 1 minus alpha. Now what do you need to do next? Simplify this inequality for p, small p, to get the confidence interval. Okay,
Yes, sir.
do it.
Yes,
It's
sir.
a very lengthy expression given in the lecture notes. You can see there. I will write a simplified expression which is all right for large n. If n is large, then you can use a simplified expression that is p cap minus z alpha by 2, p cap minus z alpha by 2 into square root of p cap. Q cap is 1 minus p cap, okay? P cap q cap over n. Yes, p cap q cap over n. Similarly, right limit for the confidence interval is p cap plus z alpha by 2 square root of p cap q cap over n. This is the case when n is quite large. Okay. You can check it from the lecture notes. So this is the 100 into 1 minus alpha percent confidence interval for the population proportion P. Okay. Now let's do a problem on it. In a random sample of 500 families having television sets in Delhi, it is found that 340 families subscribe a particular channel, say HBO, 350 families, 340 families subscribe the channel HBO. Find a 95% confidence interval for the actual proportion of families, means P, that subscribe this channel. You understand the problem? A sample of 340 families is given. Sample proportion, you can say, is given that subscribe this particular channel HBO. Now you need a 95% CI for the actual proportion of families who subscribe this channel. So what is given to you? Okay, one more thing I should tell you. This sample is given from 500 families. Means 500 families are surveyed. 340 are found to subscribe the channel HBO. So what is the sample proportion success?
340 over 500.
340 over
340 over
500.
500. So that is the value of your P cap in this formula. Okay, 340 over 500. You can find it. It is 0.68. You can write Q cap also. It is 1 minus P cap. That means 0.32.
0.32.
32.
Now you need 95% confidence interval. So you need Z 0.025. Z 0.025. This is 1.96. Okay. So all necessary things are with you. Just you need to do the calculation. What is the interval in this case? Is it 0.63912, 0.7209? Just check it. But you have understood the idea, right?
Yes, sir.
Yes, sir.
Sample proportion is given. From that, you are estimating confidence interval for population proportion. Same way, you can find confidence interval for difference of population proportions. All right. For difference of population proportions. So in that case, what you would be given? Sample proportions are given to different binomial populations. Okay, let me describe that. That we discussed in the previous lecture. Difference of population proportions, P1 cap, difference of sample proportions follow normal distribution with mean P1 minus P2 and variance square root of 1 P1 into 1 minus P1 over N1
N1.
plus P2 into 1 minus P2 over N2. Difference of sample proportions follows a normal distribution with mean P1 minus P2 and variance this. So from this you can write standard normal variable. And you can use that to write confidence interval for P1 minus P2, means difference of the population proportions. Okay, so it's also a matter of calculation. You can do it yourself. And one example is also given in the lecture notes. Please read that and do yourself. Okay, so I don't think I need to discuss that. You can do it yourself.
Yes, sir.
Yes, sir.
Yes, sir.
Now let's see one more thing that is important. One-sided confidence bounds. One-sided confidence bounds. Or you can call them one-sided confidence intervals. What does it mean? Suppose a random sample of size n is taken from a normal population. Let's do one case, then it is similar for others. Suppose a normal population is given and from which you have taken a random sample of size n. So you know that x bar follows, the mean of the random sample follows a normal distribution with mean mu and variance sigma square over n. Okay, suppose in that normal population, mu is not given, sigma is given to you. All right. X bar is following normal distribution with mean mu and variance sigma square over n. Z alpha, you understand, is what? Value of Z, value of Z such that probability of Z to the right of Z alpha is how much? Alpha. Okay. So what is the probability to the left of Z alpha?
1 minus.
1 minus
1
alpha.
minus alpha.
Can I write this statement x bar minus mu over sigma over root 1 because it is a standard normal variable? Its probability less than Z alpha is 1 minus alpha. Correct? Just simplify it for mu. See what do you get. You will get mu greater than x bar minus Z alpha sigma by root n is
Yes,
equal
sir.
to 1 minus alpha. Correct?
Yes, sir.
Yes,
Yes,
sir.
sir.
Now notice this. It means probability of mu greater than this is 1 minus alpha. Probability of mu greater than x bar minus Z alpha times sigma by root n is 1 minus alpha. So can I say that 100 into 1 minus alpha percent lower bound for mu is x bar minus Z alpha times sigma by root n. Am I right?
Yes, sir.
Yes, sir.
Okay. So this is one-sided confidence bound for mu. Similarly, you can find one-sided confidence bound for other population parameters. What would be 100 into 1 minus alpha percent upper bound for mu? Similarly, this is lower bound. What would be upper bound? You can just reverse this inequality and do your calculation. You will get plus here. Okay, you can check it yourself.
Yes, sir.
Yeah, this would be 100%, 100 into 1 minus alpha percent upper
Upper bound
confidence
for me.
bound. So this is how you find one-sided confidence bounds. Okay.
Yes, sir.
Problems are simple on these. You can do yourself. one more thing I want to discuss before I finish today. Okay. In case of normal population, what is 100 into 1 minus alpha percent confidence interval for population mean, where sigma is given to you? First case that we have discussed. See it back. It is
X bar minus Z alpha by 2.
X
sigma,
bar minus Z
right?
alpha by 2
X
sigma
bar,
by
X bar is the central value. You can say X bar plus Z alpha by
Z
2,
alpha by 2 sigma by
sigma by root. This side X bar minus Z
minus Z
alpha.
alpha by 2 sigma by beta.
Okay. So this is the 100 into 1 minus alpha percent confidence interval for mu, right? So in this, can you tell me what is the error in measuring mu? This is the error. Because either this is plus or this is minus. Central value is supposed to be mu.
Yes, sir.
Let's
Yes.
denote this error by E. So suppose error is given to you in advance. What is the sample size for the given error? Just simplify it. You will get a formula for it. See what do you get.
N is equal to Z alpha by 2 sigma by E whole square.
N equal to Z alpha by 2
Sigma by E
sigma by E whole square.
whole square.
Whole square.
Okay, so sometimes a problem is given where the size of error is given to you in advance and what it is asked, what is the sample size. So it's a simple problem. You note Z alpha by 2 sigma is also given in the problem, error is also given. Just use it to find the sample size. Is that fine?
Yes, sir.
Yes, sir.
Yes, sir.
Okay, so these are the points that I wanted to discuss in this particular lecture. Hope you have understood whatever I have explained. So, whatever I have discussed today, in all those cases, what is important? This statistic, the involved statistic according to the given situation. If you are able to recall the correct statistic, then you can easily write the confidence interval. So, on each case, you need to solve at least one problem. After that, you will be confident for doing confidence interval problems. And one more thing, the statistics that you have used here for finding confidence interval, same statistics are needed for hypothesis testing. That we will do in the next lecture. Okay, so I will suggest you to make a list of all statistics that we have used for finding confidence intervals. Those will be useful for understanding hypothesis testing problems. Is that okay?
Yes, sir.
Yes, sir.
Yes, sir.
Okay, so we will meet in the next lecture. Thank you.